My dear students, today we are introducing you the chapter on magnetism. Of course, the chapter, the subject content is the same for all boards of examination, especially for CBSE students. We find that there are certain aspects which are specific in the curriculum. However, a basic knowledge about magnetism, how magnets are there, we should be in a position to know. Naturally, the iron core, the basic structure of magnetism, starts from Fe2O3. That is, we find that this iron oxide was first observed in Magnesia in Greece, and it had got a special property of attraction, and it had also a directional property. In the initial minutes, we'll be discussing about the basic structure of magnetism. Then we will try to provide the basic law, the units, and how we are going to do with the numerical aspects. Because in most of the competitive examination, a minimum of 2 questions, that is, this magnet, the natural magnet, and magnetism produced by electricity, together combined, they take it as a unit and they are trying to put some questions in that. So, our main intention is to know from the fundamentals how the basic property of the magnetism, that is natural magnet, the bar magnet, all of you may be knowing, in the laboratory you could have seen this magnet. This magnet, when I am keeping it here, we find that it just attracts, or now you see it is repelling. Supposing this magnet is kept like that, it is getting attracted. So this is a simple bar magnet, we say. This bar magnet has got a dimension, and we find the geometrical length from this one end to another end. We are all trying to know much better in this particular class. So, why magnets repel, why magnets attract, and what is the basis or what is the theory involved in that, we should be in a position to know. So, remember, this iron oxide is the core that is responsible for the natural magnet. And therefore, the two properties that we are trying to provide here will be the attraction property and the directional property. First, let me take the directional property. When you suspend such a bar magnet, you will always find that one tip will be pointing towards the northern side of the earth. The other end will be pointing towards the southern side of the earth. That which point towards the northern side we call as the north pole. The other pole is called the south pole. How do we call that? For that, we have to understand basically earth, if you take, it itself is a sphere. We find that this is rotating about its own axis. This axis we call as the geometrical axis. Here we always call that as the north. This we call as the south. But this earth itself is the embodiment of all such elements. Therefore, the earth that is floating in the space itself behaves as a magnet, which is responsible for this earth's magnetic field, which is prevailing on the surface of the earth. You know that this magnetic field, the force of this magnetism is evolving from the northern direction and it is going towards the southern direction. If you just take, we find that this is the geographical axis. But when you say magnet, we find that this magnetic south of the earth is situated more or less near the geographical north. This is geographical north, this is geographical south, magnetic south. And the magnetic north of this earth, if you consider it as a magnet, is situated somewhere here. The line joining these two axes, the poles, this we call as the magnetic axis of the earth. This is the geographical axis. So what happens exactly is when you suspend a small bar magnet, when you suspend a small bar magnet, we find that this magnet also has a north pole and it also has a south pole. By the attraction property, like poles repel each other, unlike poles attract each other. You see, this small tiny magnet which is suspended freely has its north pole attracted by the magnetic south pole of the earth. Therefore, this always indicates northern direction. The magnetic south of this tiny magnet is attracted by the magnetic north of the earth, which is situated near the geographical south. Therefore, this is always pointing towards the southern direction. Hence, we call this as the magnetic north and magnetic south. The north pole and the south pole. When you consider this, we say here in this magnet, this particular dot that is represented here by a small paint mark will be always the north pole. In the compass, you will see that the needle will have an arrowhead that will indicate the northern direction. So, when you take another bar magnet, this also has that particular thing, and when I just keep this particular thing, now this is repelling. When I just say the southern direction, it just attracts. This is exactly the attraction property of the magnet. Another important thing that you should try to remember here is that if you take a magnet, if you say this is northern direction, this is southern direction, if you just cut that and if you are going to have this, then again this becomes north, this becomes south. Whatever be the simple divisions that you are making, each one will be having a north pole and a south pole. Okay, sir. By what quantity, by what physical property we define this ability to attract? We call that as the pole strength. So, pole strength, we say, is defined by the unit called Weber. Now, in natural magnet I am talking about. Supposing if you take a piece of wire, pass current through it, it also produces a magnetic effect in that coil. Then that is electromagnet. That also has the north pole, the south pole configuration. We are going to deal in detail in the next aspect. But here you try, and there we will be saying ampere meter will be the unit for that pole strength, because current flows through the unit length. We will be in a position to understand and we will try to say that. But here we are trying to know about the physical structure of the natural magnet. From this end to this end, when you connect these two lines, what happens? That is called the magnetic axis. So when you just take the central point, that point will be a null point, because when you shrink this magnet ns, 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 etc., here a point will occur where you will neither have north pole experience or south polarity experience. So what happens? This we take it as the 0 point. And actually, when you define the physical length, the geometrical length of this magnet, if you take as L, the magnetic poles are available slightly in the interior portion of this magnetic structure. Therefore, if this length has to be considered, that magnetic length L will be lesser than the physical geometrical length of the piece of the magnet. Further, when you want to consider any distance to be calculated, it should always be calculated from this center of the magnet. That means in all the calculations, you will be coming across one thing called the semi-length of the magnet. Because when you take the test magnet, the unit north pole, because the north pole of any bar magnet will repel this unit north pole having magnitude 1 Weber. That is called unit north pole with a force. What is that force? That is defined by Coulomb's law. Therefore, we find that the unit north pole from here will be having or experiencing a repulsive force. That is the force due to north pole. But this north pole that is situated here, the test pole, actually remember there is no unit. Every object will be having two things. But this is hypothetical. So this unit north pole, the influence by the south pole of the bar magnet will be in this direction because it is attracting. That is the force due to south pole. We say that. That means this distance, if you calculate from the north pole, it will be like this. And when you take this particular case, this is the total distance that you have to consider. And the distance to be considered from this here means from the center of the magnet, then the semi-length of the magnet should be known. That's why we always consider the length of the magnet as 2L for mathematical simplicity to avoid any complexity and fractional aspects, otherwise 2D. Either commonly in various textbooks, this length of the magnet will be represented by 2 small l or 2 small d. Therefore, the semi-length can be either L or D. So remember, in this aspect we have learned the length. Capital L represents the geometrical length. You should always remember that L is always greater than 2L. 2L is the total length of the magnet. Otherwise, total 2D you can derive take. The distance between the north polarity in the magnet and the south polarity in the magnet. So this is a simple structure, and this pole strength is represented by a small letter m. Okay. When you take the small magnet, a bar magnet, and when you say this is the north pole, this is south pole, etc., this is the center, we find that the imaginary lines of forces are called the flux. The field lines of activity is generally called as flux. The light rays we call as lux. Field lux is called flux. So this particular thing will emanate from north pole and terminate at the south pole. This will be going like that. And this also goes like that in this direction. We find that these are all the aspects. You should try to remember the direction. So the field lines in the proximate, close thing may appear to be spherical, but when you consider a larger distance, they will appear like that. So when you have got such lines of activity, you see number of multiple choice questions they give like that and all, they put this point as A, they put this point as B. Note the polarity of A and B. I told you the magnetic lines of activity emanate from north pole and terminate at south pole. And when they are all parallel, we say that it is a uniform magnetic field. This area covered by these lines of action of this magnetic aspect is called what? The magnetic field. The magnetic field here we will consider as the flux density, the force per unit area F by A. We call this aspect as a Tesla. Remember, this is Tesla. The Tesla, we call that as the unit represented normally by the letter capital T. So the pole strength I told you as Weber, and this one as this particular thing. When you say what is the exact force, that is defined by Coulomb's law of magnetism. When you say that there is a north pole, there is a south pole separated by a distance d meters, then what happens? This has got a pole strength of m1, this has got a pole strength of m2, there will be an attraction. If I do not know what are these magnetic poles, I generally define either the force of attraction or the force of repulsion. This force of attraction may be proportional to the product of the two pole strengths and inversely proportional to the square of the distance between them. In most cases, even electricity, we find that Coulomb's law of attraction or repulsion between the charges, like charges repel each other, unlike charges attract each other. We will later know that the origin of that electron as well as that of this magnet by Weis theory will be the same. We find that this F proportional to m1, m2 divided by d square, or when you make it as an equation, you introduce a constant. That is a physical constant. Of course, it will also have a component of mathematical constant also. This F equal to mu 0 by 4 pi. I am introducing some symbols here. m1, m2 divided by d square. What is this there? This is a constant. You see, the force is that which is acting between this part and this part, where in a medium. The medium may be vacuum or air or any other medium which is different from that of either air or vacuum. Then I have to define that in general this mu, the ability for these magnetic lines of attraction or repulsion to pervade through, that is called permeability. What is that thing called as a permeability? So the permeability represents the general aspect. This has got two components. One is called mu 0 into mu r. This is called absolute permeability. This is called like epsilon 0, epsilon r relative permittivity in electricity. This is absolute permeability. This is called relative permeability for different media. For air or vacuum, it has got this particular value that is 4 pi into 10 power minus 7. This mu r, a number, it is just a ratio. It cannot have any other unit, but mu has got unit. It is a physical constant. So F equal to mu 0 into m1 m2 divided by 4 pi d square. This forms the basic structure. Now, as I have told you earlier, this multiple choice question. Now you tell me, what is this A? A is the North Pole. B is the South Pole. Try to remember, the magnetic lines of action go like that. Another important property is that these lines of forces never intersect. I will be giving you the reason for that also. But now as it is, you take this particular thing. So the basic structure of magnetism, what we have learnt now with this structure is, first, the attraction and repulsion property. We know that like poles repel each other. Why the suspended magnet always indicate the north direction and southern direction, not east or west or something like that and all? That we have learned. Earth itself has a huge magnet and thereby it is moving like that and all. And further, we have also told you the geometrical length and the magnetic length. Why we consider the total distance of the magnet as 2L or 2D instead of taking it as L itself? Because we are always trying to find the distances of any other point from the midpoint of the magnet. Therefore, the semi-length is more useful here for all practical considerations and calculation. And for this basic natural magnets, we consider the test magnet as the unit north pole. Of course, it is hypothetical, I told you. We define the pole strength given the symbol small m with the unit Weber as it is now. The magnetic field represented by Tesla, V Tesla, the force per unit area we told you, and the Tesla capital T being the unit for that particular thing. So what happens when I place a small magnet here in the magnetic field? I told you the magnetic fields of action starts from whether it is a linear bar magnet or a U-shaped magnet. We say that this magnet is being influenced by this magnetic field strength. So, when you define, you take Coulomb's law of attraction or repulsion. If M1, M2 be the pole strength of the two small magnets that you are considering at a distance d meters away, large distance compared to the semi-length of the magnet, we find that either the force of attraction or repulsion is directly proportional to product of the pole strength, inversely proportional to square of the distance between them. So it is called the inverse square law, Coulomb's inverse square law. So when you say that this force is proportional to m1 m2 by d square, when you equate it, we say that F equal to mu 0 by 4 pi into m1 m2 by d square. And the constant that is getting introduced here is called permeability. If it is air or vacuum, it is represented as mu 0 having a value 4 pi 10 power minus 7. Whereas, you can very well understand this thing. See, it is a simple concept. The force in Newton, this d square meter, Newton meter square by Weber square. This mu 0 value. When you consider the force experienced by a unit pole, even then 1 Weber becomes the unit for that. And we also initially introduced this equation, a basic equation, remember, mu equal to mu 0 mu r, where mu 0 is the absolute permeability, mu is the general permeability, mu r is the relative permeability. So mu 0 refers to either air or vacuum. Mu r represents any other medium other than air or vacuum, because all these forces are experienced in the environment, otherwise called the medium. Now the question is, when a small magnet is suspended in a magnetic field, what exactly is taking place? Let us try to understand that. And we will be in a position to know yet another expression, what is called the magnetic moment, which will be more useful in most of our problems and in defining the basic properties, either be natural magnet or electromagnet. That is, magnetism produced by passing current through a conductor. So let us try to understand that there is a uniform magnetic field. I told you that this is a uniform magnetic field that I am having. How do I say uniform? Because the lines of action are parallel. If I just have a line like that, it is not conveying the meaning of a magnetic field. I should have the directional property. That means the field lines are moving from the northern side to southern side. This is how it is there. This is the basic aspect. This is the magnetic field. This magnetic field has got a strength, field strength, I told you, B Tesla. Let me take that. Now, supposing if I suspend a small magnet oriented at an angle theta, you see this is the thing, about this axis. Now, this magnet is being suspended to an angle theta. Let me take that. This has got a pole strength M. Remember, for a magnet, the north pole and the south pole can have equal pole strength. Remember that for a magnet, the pole strength of the north pole of the magnet and the south pole of the magnet will be the same. So at this point, you try to remember this magnetic pole here, which is north pole, and this, if I consider as a south pole of the suspended magnet, is experiencing a force of attraction towards this southern side. This experiences a force of attraction towards the northern side. So, we find that this field, the magnetic field B, is inducing a moment. What is moment? A turning effect. That means we find that there is a force MB. This is a force. This MB is the force. Here also the same strength MB. So this body is now, you see, when I have this particular thing like that, if I have a structure like that, one force repelling here, one force attracting, this body is turning. That means this will have a moment. What is that moment? That's the torque, rotating force. That means we try to find this magnetic moment. We call that as capital M. This is nothing but the force into perpendicular distance. When I say that this is exactly the force into perpendicular distance, I find that I draw a projection here, and from here, then this particular distance is the perpendicular distance. That is, if I consider this point as A, then SA will be the perpendicular distance. But I know that this particular length of the magnet is 2L. The magnetic length of any small magnet I consider as 2L. Now, these are all the situations that are available. This is the perpendicular distance. Therefore, how do I consider this value happens to be F into SA. This will be the force. Can you just understand that? What is the value of the force that is available here? MB. And what is this SA? That is equal to into, I find that in this triangle, if this is theta means this is theta, we can very well understand that what is sine theta equal to? For sine theta, what is the thing that I can consider? The perpendicular distance. That's what I want to know. The opposite side, NA, sine theta equal to, can you just understand that? From here to this is the slanting distance. If we take this particular distance, NA, opposite side by hypotenuse side 2L. Therefore, this NA, actually this should be written as what? NA. Because this is the vertical distance, that is the perpendicular distance between this pole and this pole where the two forces are acting. Remember that. So, this in the contradiction we will be taking. So, we can very well say that NA will be equal to 2L into sine theta. So, when you take this value 2L into sine theta, we can just group them like this. What is that? We have got this M, the pole strength of the magnet. This 2L, the length of the magnet. You cannot change the pole strength of the magnet. When you take a particular dimension of a magnet, and if you are declaring it, this M becomes a constant. There's a constant. This 2L, the length of the magnet, this is not also undergoing any change. Therefore, this itself we call as capital M. Then we say B, then we say theta, sine theta. This particular thing we call as the torque, the rotating couple acting in the magnet. This rotating couple, how I am going to describe? That's what I was writing earlier, tau here, and then for easy reasons I have made it as M. Here I am trying to define it. That is, to define M, this M becomes a tau when B is unity and when theta equal to 90 degree, sin 90 equal to 1. So, we find that when this becomes 1, M becomes tau. It is the torque acting on the magnet placed in a uniform unit magnetic field at right angles to the direction of the magnetic field. So when theta becomes a 90 degree, we have to remember that what are all the things that they are sequencing. This clearly will give you inputs regarding solving some problems related to a magnet that is orienting along the field kept perpendicular to the field. From here to perpendicular thing, it will have maximum work done. And when it is along the field, it is so. Because theta becomes 0, sine 0, 0. The turning effect will not be there. It is already aligned. Therefore, this normal aspect, what we call as the perpendicular effect on the magnets, are more influential. And to summarize, certain basic aspects of these magnets and all, I have told you earlier, we will be having some units also. We should be in a position to remember. And we told you the force. A unit pole is a pole of that much strength which when placed at a distance of 1 meter in air or vacuum from an equal and similar pole repels it with a force of 10 power minus 7 Newton. How come 10 power minus 7? We find that 4 pi into 10 power minus 7. Mu 0 by 4 pi is there. All these configurations are trying to provide these aspects. So try to remember, you should try to underline the units, definitions, etc. So we have to consider what is the work done in a deflecting magnet in a uniform magnetic field. What are the basic properties of the magnetic lines of forces? For reasoning questions and high order thinking skill questions, this basic information is very much useful. Magnetic lines of force originate from the North Pole and terminate at the South Pole. A line of force indicates the direction of motion of the free unit North Pole in the magnetic field. Two lines of force are never intersect. They tend to shorten to straighten like stretched rubber. They tend to expand laterally or pushing away from each other. Parallel lines of force indicates a uniform magnetic field. So try to remember these basic aspects. Being the introductory aspect, I have just told you the basic fundamental things that we should be knowing, and in the next video we will be in a position to know about certain more aspects like calculation of intensity at a point on the axial line of the bar magnet, equatorial line of the bar magnet, and what is the relationship between them. These are all certain things and certain numerical aspect. To start with, we will also tell how the electronic structure in the material makes certain elements magnetic elements and other aspects are non-magnetic elements. But the next video will be more concentrating on numericals based on the fundamentals that are listed today, including Coulomb's law. And when you break the magnet either along the axis or perpendicular to it, whatever be that particular thing, what are all the various changes that are taking place, these are all often asked in the competitive examination. Thank you.